So right now we have Matt Hawthorn with us to talk about leveraging taxonomic structures in classification on large label sets, and we'll get started.
Check. Hello. Okay. Hi, I'm Matt Hawthorn. I work at Trilliant Health. We're a medical claims analytics company, so most of the data that I work with is medical claims. But the talk that I'm going to give here is about something that I came up with for a problem that we had there last year. But it's also something that's like come up repeatedly during my career, and so I was just like, it's time to build this thing that I've had a vague premonition that this thing is needed, and so I built it last year, and I'm giving a talk about it. So, like, the problem is we have tons of classification problems in applied ML. I mean, even in the age of, like, super smart LLMs and stuff, we still need to, like, route queries and classify things. And a lot of times, the target that you're trying to classify into has some sort of tree structure, some sort of taxonomy. And the characteristics of that taxonomy can vary a lot across domains. So, like, how deep is it? There's one on the left there with just one layer and one on the right with two. Or how wide is it? The branching factor on the right is 3 and on the left is 2. Or is it even like heterogeneous? Like, are there different depths at different parts of the tree and different widths at different parts of the tree? So like the evolutionary tree of organisms is much like this. It's got like way more branches under certain genera than under others. And so there's a lot of examples that I've come across while I've been working in data science. And the first one I remember is the ONOT ontology of jobs and tasks. When I worked at Snagajob, which is a job search company, that was something we used to classify job descriptions into. And this was like hundreds of jobs, but there was a hierarchy of like which high-level type of job is it, and then under that, which sub-level, and so on down all the way to the specific job. And then the nuke is a taxonomy that's used in healthcare that we use to classify providers, like medical providers, into different types, and there's hundreds of those. ICD-10 diagnoses also, these last three are all healthcare things that I've come across, and that's also hierarchical. There's a root node for like infectious diseases, and then under that, like each of those specific infectious diseases, and then under that, specific complications that go with them. And then DRG codes, diagnosis-related groups, also medical, that's used to group complex inpatient visits into like billing categories basically, and there's hundreds of those. And so all of them have taxonomic structure, and it's usually explicit. It's built into the system, into the coding scheme. Like they'll even spell it out in the shape of the codes that you're targeting. But sometimes it's implicit, and it kind of it's obvious from like natural language descriptions of the things that like there's some sort of implicit hierarchy here. But it always encodes some sort of rich domain knowledge, and like if you don't take advantage of that knowledge, my feeling is you're probably kind of leaving something on the table. And so that's what I've been feeling the whole time is like whenever I have one of these big classification problems with like hundreds of possible outputs, and I'm not leveraging this taxonomy, I feel like there's got to be some sort of prior or something I can bake into my model that would help out with that. And so, like I said, nearly all of these are things I've encountered at work. And the status quo for this is like run-of-the-mill classification. You just treat all the labels as equal, and you have a flat label set. Every class has to be learned in isolation. So imagine a linear model. Every class has a big, long vector, and in that vector is a weight for every single feature. That's, depending on how many features you have, that could be a very long description. Why not share some information between that particular class and the classes close to it in the tree, which are probably similar to it? That's why the tree exists. So we don't, but with the standard run-of-the-mill, we don't really share, a lot of times we don't have like a way of sharing statistical power between those groups. And so, yeah, if you want to, and also if you want to quantify, like, am I, at the root of the tree, am I in branch A or branch B? Like, you just have to aggregate probabilities over all the nodes, all the classes at the leaf level, all under A or under B, and that's kind of ad hoc. So why not leverage, like I said, leverage this taxonomic structure as an inductive bias. So to motivate our intuition of like, why you would do that, I'm going to play a fun game here. Guess the species. So this little guy here, just out of curiosity, does anybody in here know exactly what this is? Or like up to the genus maybe? Okay, good. That's great. That's exactly what I want. But we all know it's an animal. We all know it's a mammal. That's like pretty obvious. If we wanted to think a little more, like I tended to think this was like a rodent, but I can't see the teeth, so I can't be sure, but like I'm like 80% sure this is probably a rodent. And then what else would you need to know the species?
No split, divergent hallux.
We've got an expert here. See, we need to take advantage of expert knowledge. So, like, if you were an expert, you'd be looking at the toes and, like, the split of the nose and other things like that, the vocalization. This little guy says is known for saying wah-wah. There's, like, a whole YouTube genre of this critter saying wah-wah. And it's a hyrax. It lives in Africa. And it's technically not a rodent, which is crazy, blew my mind. Like, I actually wrote this whole talk assuming it was a rodent, and then had to go back and like fix everything. But we'll get to that. So takeaways, like, you immediately knew it was an animal and a mammal, and that was, if you tried to rationalize that to yourself, it would be because, well, it has bilateral symmetry, 4 limbs, eyes, nose, ears, hair. These are all kind of high-level features. And then if you wanted to go under that and get more specific, you'd not be thinking about those things anymore. They're just given. Like, you don't have to. You already know it's a mammal, so you're not thinking about like necessarily about hair. Maybe in certain branches, like where the elephants live or manatees or whatever. But you're getting more detailed into different features. Thinking about toes, vocalizations, teeth. So takeaways from this, like the salience of features depends on where you are in the taxonomy. So like, how deep are you in it? Which branch are you on? If you want to know if something's animate or inanimate, you're asking, does it move? If you're asking if it's a mammal, if you know it's a mammal and you want to know if it's a rodent or not, you look at the teeth and maybe the size, although there's capybara. So, and then, corollary, like taxonomic structure will help you with feature selection. If the taxonomy really does encode knowledge and it's useful knowledge, then there's fewer features required to distinguish any given branch than if you just tried to distinguish a hyrax from every other creature. But when you're doing standard classification, you're trying to just distinguish every class against every single other class. And when you do that, like a huge amount of features are salient. And so it's better to focus learning on these subtle distinctions you might find within a single branch of this taxonomy. There's an insight from active learning, if you're familiar with that field, that models learn more from like the harder, more ambiguous examples. There's more information there. So don't waste effort telling a hyrax from a lungfish. Try to tell a hyrax from a prairie dog, which is like maybe something, I guess if I really pinned people down, maybe some people might have said prairie dog. So classification by taxonomy, this also allows you to like quantify uncertainty over different levels of the hierarchy, which is something you might need to do in a case where like you don't need necessarily a point estimate, but you need to go down to some level. I know this is a rodent, but I don't know which subspecies it is. And little joke on myself there. So the main idea here is like use the taxonomy's inductive bias. Take advantage of that expert knowledge that's built into it, and you train in an ensemble in the shape of the known taxonomic structure. Each subclassifier in there has a small task. It just discriminates one particular node, the branches underneath. And then the one requirement for this framework is you need a probabilistic classifier. So, but once you have that, then all the probabilities accumulate from root to leaf via the chain rule of probability. So if you want to know the probability of being class C and you're in a 3-layer hierarchy, which has A that leads to a subclass B, subclass C, then you have these 3 probabilities you multiply. Probability of being on branch A times the probability of B given A and C given B. This should all be pretty familiar if you're into probability. And so all 3 of these would be a separate little model, a little micro model that branches that knows about that particular branch. There's a root classifier that tells you the probability you're on branch A. And then under that, there's another one subclassifier that tells you, given you're on A, if you're on B, or what likelihood you are on B, and likewise down a layer. And so here, let's go through like an example of how we train this. And this is just a super small toy example, so you can just visualize the whole process. So here's a data set on the right and the root of a tree on the left. And the classes are on the left of the table. You can see they all start with a 1 or a 2, and I've encoded that with red and green. And so the red and green there is like a synthetic label I'm going to use to train one classifier whose job is just tell me, am I in branch 1 or branch 2? And then underneath branch 1, there's another sub-branch, and it has 3 classes. And I'm going to train a second classifier that tells me, given that I'm under branch 1, what's the likelihood of that I'm in class 1.1 versus 1.2 versus 1.3. And then likewise under 2, there's a similar subclassifier there that I would train to distinguish those 3 branches. And then under 2.3, we have, again, heterogeneous structure, so we have another layer under that one class. And I'm just going to focus in on that and learn to distinguish those 2 cases. And so these are a sequence of training sets with a synthetic label. The subset where where the colored label is the subset I'm training on in each case. So I have like a little ensemble of these multiple classifiers. And then so what does inference for this look like? So at the root, let's say my model was 30% sure it's branch 1 and 70% it's branch 2. And then the model underneath branch 1 is 30, 50, 20 between those 3 branches. And then the one under branch 2 is 10, 70, 20 under those 3. And then I have my one weird little one underneath 2.3, and it's 50, 50. And so I just multiply these root to leaf, apply the chain rule, and I have the final probabilities for all my individual classes, just like I would have gotten from like a normal one versus all or all versus all classification scheme where I'm just classifying every single leaf directly. And so in this case, 2.2, if you were doing a point estimate, 2.2 would be the winner by a pretty wide margin, but you still have some uncertainty quantification there. And then, of course, you can quantify at the root that like I'm 70-30 or down below that. You can get more fine-grained information about certainty. So this is like a really simple idea, and I couldn't find anything like it just as a library I could just find on PyPI or something. So I ended up building it. I almost like don't want to take credit for it because it's kind of such a simple thing, but I couldn't find it, so I built it. And so I wanted to go into a little bit of technical discussion about why you would do this. Aside from just you did a test and the accuracy was higher. So the cost for most ML algorithm training it's usually linear in features and samples and classes. And so if you have a hierarchy of classes, let's say you just have an ideal structure of data where the class structure is branch factor B, depth D, then you have B to the D classes. So I just substituted that there. So the ensemble training cost, at the root you're training on the whole data set, but there's only B classes, not C, which is this exponential B to the D. And so you have that's just substituting the regular classifier cost. And then at the level below, you have less data, N over B, but you have more classifiers. That's why that extra B at the end. And then this just recurses down. And if you follow this, every layer costs the same. And then you add them all up, and you get these 2 numbers. The base model, like standard ML, would be N times F times B to the D, but then with the ensemble, it's just N times F times B times D. So you took an exponent and you moved it down to as a product. So generally going to be lower cost. And in practice, because like that discussion we had about the hierarchs, like you can prune more features at each layer. So in practice, F will be smaller too in each subclassifier, which is kind of neat. So this can be a big boon for just like if representational efficiency. So if training cost is a problem, then this could significantly lower that. It's also flexible, so you could have like a sort of router at each classifier at each node that picks a classifier architecture depending on the nature of the data under that node. So like let's say it's like a really hard, it's known to be a really hard problem to distinguish these particular subspecies in this little branch. We can use something nonlinear there. Maybe at the root it's really easy to tell like fish from birds, so we just use a linear model there. And then you can also just drop this in. If you have a model that's a baseline, it's just working, just plug it inside this ensemble and see if you get an improvement. Same architecture, same hyperparameters, and just see what happens. The only requirement to do that is that the base model is probabilistic. And then so scaling this up, you can, because training is cheaper usually, you can train on more data, and data is the great regularizer. If you have more data, usually you can do better on your problem, assuming your architecture represents the data well. And the training can be embarrassingly parallel as well across all the subclassifiers, because we're just subsetting data and training on different bits. So we even distribute training to different machines at Trilliant for one of our models. And so there's one optimization you can do as well. Like if you don't care about quantifying uncertainty across all levels and you just care about a point estimate, you can prune. So like if I'm 70-30 on this tree at the root, then the max probability, the max min probability, the min max probability on branch 1 is 35%, 0.35, because I can't go any lower than just splitting that 70% equally. And the max any probability could be on branch 2 is 0.3, because chain rule, everything under 2 is less than 1, and I'm multiplying it by 0.3. So I know I can just completely prune branch 2 because there's no way that it could exceed the lowest possible max probability on branch 1, and then I have more efficient inference. There are some caveats to this. If you've been thinking critically while I go through the training, you probably observed that like the subclassifiers train on subsets of the sample of the feature space. So they're probably ill-calibrated outside that space. Like the one that distinguishes rodents probably has nonsense to say about fish. So there's some hand waving here, but basically if your root classifier is really good and it puts like a lot of probability mass on the right branch, then this problem, it's not a huge problem because it doesn't really matter what the subclassifier says because there's only so, again, with this pruning example, there's like only so much probability that could go on any of the branches under 2. So that's kind of my hand waving, but I did come up with sort of an elegant solution to this. I didn't end up needing it, but I built it into the tool, into the library. But like the more certain you are about, the more certain your parent is, the more certain maybe that you can afford to be, and the less certain your parent is, maybe the more you should hedge your probabilities. And so I used like a temperature rule, which if you mess with LLMs, you're probably familiar with this. But instead of it being a fixed temperature, it's variable with the parent classifier confidence above you. So if the parent classifier is less confident, you just sort of spread out and hedge and say, I'm not, like I can't put 100% of my probability on this one class. Like I haven't found it useful, but again, I tried it out and it was fine. It didn't hurt it. It didn't help it really, but it's built in now. And so here's a slightly more interesting example. This is synthetic data. 4 levels, 6 branches at each level, so that's 1,296 classes, and these are just Gaussian blobs. This is just like a toy data set again, but just to help you visualize this. So this is, you can see the outer layer, each of the big hexagons is one layer in the first branching of 6, and then under each of those there's 6 more subhexagons, and then under each of those there's 6 more, and then each of those is a little ring that looks like kind of a blobby donut, but it's really 6 classes that are RGB encoded that are all slightly distinct colors. So there's 1,296 little blobs here. So let's try like fitting just like a standard like linear model on this. I'm not regularizing it because there's only 2 features and they're both salient, so I don't need to. I'm gonna give it all the cores I've got, and I train it, and it took a little over a minute. I think there's 26,000 or so rows here, and it was 77% accurate roughly. So let's see how it does in terms of its like confidence in the feature space. So this is encoding model confidence at each point in the feature space, but only on the in distribution points. So like only where there's data. And you can see it, like the colors still sort of correspond, but the picture is very transparent. So there's not a lot of certainty anywhere really, except in a few spots. And here's how it extends to the rest of the space. So it gets a little weird on the outside there. It should, because like there's nothing the model could know about that stuff. But let's look at when we wrap it in the taxonomic ensemble. So here's the code you would run. We have an open source repo where we host this model that I'll link to at the end. This is the import, and you would just take your that clone CLF. That's our old classifier, same architecture, nothing changed. And I'm just cloning it, sticking inside this ensemble. And the class tree there is just specifying like what's the structure of my label space. So it's just a nested list of lists all the way down to my leaf classes. And I'm going to fit that thing. It just has the same interface as any old standard sklearn interface. And that one got an immediate accuracy boost. It took 6.7 times less time to train. This was a year ago on an Intel Mac. I have an M4 Mac now, so I don't know how it would do. But benchmarks are funny like that. But anyway, it was quite a lot faster, and I got an immediate boost in accuracy. Not a huge one, but like if you frame it in terms of error reduction, it was almost a 30% error reduction with like no hyperparameter search, no other optimizations or anything. And then, so let's look at how that one predicts and what its confidence is like. So So this is what that one looks like on the same feature space. So very crisp. Every single class is well covered and colored in very confidently. So there's no fuzzy like uncertainty really almost anywhere where there's data. And then extending out to the rest of the space, it just has a nicer looking shape. I can't say much else about it other than that. It shouldn't have anything rational to say about all the space out there because there wasn't any data there, but it's kind of neat how it extends sort of linearly in these nice shapes. And so there's like a real world example that motivated all of this was a problem that I have at Trilliant, which is diagnosis-related groups, which I mentioned earlier. There's about 840 of them. They classify like complex medical care by category. So if you go to the hospital, there's usually a DRG. If you stay there, there's usually a DRG code associated. These are classified into like 25 branches that are called major diagnostic categories. And there's 2 to 5 layers in this whole tree all the way down to this really specific treatment. And inpatient medical claims are supposed to have these, but if you've ever worked with medical claims data, you know it's like super messy. People don't fill in fields. There's fraud. There's people trying to like hedge their bets in billing and like make the insurance company argue with them about what the right code is. So it's not filled in all the time. It's actually missing a lot. And our customers need them for aggregating care across categories. So we need to impute them. Where they're applicable. Again, they don't apply anywhere but like inpatient claims. And so our data set here is like over 100 million inpatient stays, tens of thousands of features because we've got diagnosis codes and those ICD-10 procedure codes. So we've got like tens of thousands of possible features, 840 classes. Massive imbalance, like the most common DRG, like a hip replacement, is like 1,000 times or multiple thousand times more common than the least common. So it's kind of a tricky problem. So what we did was we just fit like a baseline model just to test the kick the tires on this thing, just like baseline model, no hyperparameter optimization. And then we stuck that inside the ensemble and got an immediate boost in accuracy, about 11% raw accuracy and a 33% error reduction. So that was like a huge win. And it trains faster because it's like all the stuff that I talked about earlier. And then the training, because it trains in less time, we can train it on more data. And because we can parallelize training, we can distribute the training and like get a lower wall time. Like there's the same amount of compute, but less waiting. And then with more hyperparameter optimization, just all the usual stuff, we got it up to 83.4 raw accuracy. And then if you count like within the bottom, like right above the leaf level, we're 91.5% accurate. So that's like, we know all the way down to the specific type of medical care, but we don't know, the bottom layer of DRGs is like how complicated it was, like were there complicating conditions associated with this particular visit. And that one's a little tricky, again, because of like missing data and stuff. So big win there. And that's really what motivated this whole thing. And you can look at our open source repo there at the top, and that's where this code lives. And you can also see Hyrexes don't have the usual rodent teeth as well. And then there's my email there if you want to have any questions. I would love to hear people, like if you have a problem like this, because the code exists and you can try it out. I would love to hear from people that have similar problems, because I've only really like used it in production one time on this one big problem. And I'd be curious to know if it works elsewhere. And that's pretty much it.
Awesome. Thank you. We have a little bit of time for questions.
I've made similar models to this I've made a similar model to this with a similar sort of problem, and I was thinking, like, as an example with the like an issue that could happen that I kind of ran into. It's like if with the animals you had dolphins and sharks, and you sorted this, and you had like a blurry image of a dolphin, then it might say that that's more likely to be a fish. And then because dolphins would only be sorted in the mammal category, it's not going to figure that out as well.
Yeah, that's right.
And so, like, I think, like, in order to get this sort of model to do that well, I think you kind of just have to have a lot of dolphin images to train on so that it can say there's at least some probability of it being a mammal. But I think, like, if you just did like a decision tree classifier instead, like a classical one of that, it could do better for that kind of case, I was wondering, do you like have a way that you can like balance the benefits of both of these and like have like something where it can take care of that sort of edge case and like do well on that?
Okay. Yeah, I think this probably underscores a really big point in my mind, which is that like features matter a ton. And so, yeah, if you are classifying images and all you have is pixels, then in that case, and if your images are blurry, then that's a really hard case. But if you're like a biologist and you have like structured data about a species as well, you know, there's lots of things about mammals that you can't see just on the outside. Like with the hyrax, we can't tell it's not a rodent because it's not always showing us its teeth. So yeah, features really matter a lot, and you know, and that also gets into domain expertise. That's all that I can really say about that. I'm sure that there are problems where this definitely wouldn't work because of the ill-calibrated problem. And I just haven't, I just tried it for this one problem because I was like, I feel like it should work. It was just a gut feeling, and it just worked really well for this one problem. So I don't have anything smarter to say about that.
Any other questions? One in the back.
Like, did you have to deal with changing like taxonomy much? And if you have a changing taxonomy, like does your system, is it easily updated? You have to run like your classifiers all over again, but I'm just kind of curious if there's a trade-off with systems that have highly changing taxonomy.
Yeah, I guess thankfully in medical coding systems that they're pretty static. But if you did have a change, then yeah, you'd have to retrain and repredict. So there'd just be with this framework, there'd be no way around that. But I'd be curious to know if anybody has thoughts on that. But it's not something that I've had to think about because the medical world is pretty, there's a lot of perverse incentives in medical claims, and there's a lot of people set in their ways, and things tend to, like, once they're created, they tend to stay the same. But that's an interesting question.
Excellent. All right. Thank you very much, Matt.
Thanks.